Okay, we're ready to look at some examples of higher derivatives here. And in this example, we're told to find the first three derivatives of f of x equals x squared plus 3. So that's our original function. Let's write that down. F of x equals x squared plus 3, nothing too complicated there. And so to take our first derivative, that would mean we are finding f prime of x, or if you want to go Leibniz on it, could do d dx of f of x. So we are taking the derivative of x squared plus 3. And this one is a quick power rule. We're going to bring that 2 down from the exponent, bring it out front as a coefficient. And then we'd have 2x to the 2 minus 1 would be first power, so 2x. And then plus the derivative of that constant, 3, which has a derivative of 0. And so we just end up getting 2x. Okay. Now, if we want to find f double prime of x, the second derivative, we are taking the derivative with respect to x now of the derivative that we just found, d dx of f prime of x. So that would be d dx of the function 2x. And so that would be our constant multiple. 2 is multiplying x, so 2 times derivative of x is just 1. And so we end up getting 2 for that second derivative. Now we want the first three derivatives, so here is f triple prime of x. And that we're going to take the derivative of the second derivative. So you go one prior, take the derivative again. So d dx of f double prime of x. That'd be the derivative of what we just found, which was 2. And the derivative of that constant is just 0. So there are the first three derivatives of our function. So original function is x squared plus 3. First derivative is 2x. Second derivative is 2. Third derivative is 0. Now, it's also kind of worth noting what would have happened if this problem had asked us to go any further with this. So you might want to make yourself a little note here. Note, if we had to go any further, like taking the fourth derivative, the fourth derivative would have equaled 0 as well, because to get the fourth derivative, we would have taken the derivative of our third derivative, the derivative of f triple prime here. Derivative of 0, well, still just the derivative of constant, so it's still 0. So the fourth derivative would be the same as the fifth derivative and the sixth and everything else after that point. All the derivatives after this would equal 0. So let's take a look here graphically at what we're doing. All right, let's make a quick little graph of our function and its derivatives. Okay, let's set up some axes here. And let's put in our original function f of x. That's x squared plus 3. So that is the parabola x squared that's been moved up 3 units. So it's got a vertex right here at 0, 3, and then opens upward from that with the classic parabola shape. 2, 3, 4. There we go. 2, 7. -2, 7. All right. So there is f of x. Okay. Now, the derivative of that is f prime of x, that's 2x. So that function is going to be linear. That's a line with a slope of 2. Okay, so let's put that in green here. All right, goes through the origin, has a slope of positive 2. Okay, up 2 over 1. All right. There's f prime of x. And just looking at those two graphs alone, remember that the derivative function values are going to give you the values for the slope of the tangent line to the original function f of x. Okay, so note here, f prime gives the slopes of tangents to f. And so we can see kind of the two halves of our function here. For x values that are greater than 0, the derivative f prime of x, this green function here, has a positive value to it. So the tangent line to the original function should have a positive slope. And you can look at the original function all through here. And if you imagine putting tangent lines to the function, to that curve along those values of x, all of those tangent lines would indeed have positive slopes. So the derivative is giving us the right information there. Now, also for values of x that are less than 0, it's going to do a similar thing. Notice how our first derivative is negative over there, has all negative values. And if you imagine putting in some tangent lines to this curve for negative values of x, all of those tangent lines would indeed have negative slopes. So negative values here, negative tangent slopes here. That's our relationship between the original function and its derivative. Now it works the same way for higher derivatives. If you take f double prime, that's going to give the slope of the tangent to the function prior to it, which would be the first derivative. Okay, so f double prime gives slopes of tangents to f prime. Now, if you imagine putting in a tangent line to f prime here, f prime is just a line itself. So if you try to go tangent to that line at some point, you are actually just going to be lying right along that line itself. So notice how the slope of the tangent line to f prime is actually just going to be a slope of 2. Okay, slope of 2, because the tangent line just lies along that f prime function. So that actually comes in when we look at f triple prime. F triple prime gives the slope of the tangent line to f double prime. So we should put f double prime on this graph as well. Okay, f double prime is 2, and that is the slope of the tangent to f prime. So our slope anywhere along that f prime line is just a slope of 2, and that's why f double prime is this constant function, f double prime of x there. And then you can see for that, the slope of the tangent to f double prime, if we come in tangent to this orange line here, the horizontal line y equals 2, the tangent to that would just lie right along that line as well. So the slope of that tangent that I'm drawing in right now is a horizontal line itself, so the slope of that is 0. M equals 0. And notice how that is our third derivative function. So the 0 there corresponds to this tangent slope here, and we get our f triple prime function, which is just a constant right down here at 0. F triple prime of x. That's also why, again, any subsequent derivatives, the fourth derivative, fifth derivative, etc., those are all just going to equal 0 because that would be representing the slopes of tangent lines to this function here for the fourth derivative. Okay, so that tangent line would come along perfectly horizontal still, slope of 0. The fifth derivative would still be a nice horizontal tangent, slope of 0. And so all the remaining derivatives are just going to equal 0. But that's how we find higher derivatives, and graphically that is the relationship between all of these functions. Each next derivative is just giving the slopes of tangent lines to the previous function or previous derivative.